super happy chatting. Okay, well, I think we'll get started. We seem to have stopped the constant stream of people. Tēnā koutou katoa. My name is Suzanne Woodward. I'm the Associate Director of Research Impact at the Public Policy Institute. And I have the privilege of welcoming Professor Will Steffen tonight, who I imagine, if you were here, doesn't really need an introduction, but I'm going to give him a brief one anyway. So Will was the director of the Australian National University Climate Change Institute. He was a member of the Australian Climate Commission. He was the executive director of the International Biosphere Program. He has a BSc in Industrial Chemistry and an MSc and PhD in Chemistry from the University of Florida. He has published extensively on climate science, and his research interests range over climate change and Earth system science issues with a core focus on sustainability. He's written on adapting land use to climate change, bringing human processes into the modelling and analysis of the Earth systems, and the history of and future prospects for the relationship between the natural world and humans. And he's particularly well known, obviously, for his work on the Anthropocene. So I would like to firstly thank Vector for supporting this and their willingness to share Will with us. And please join me in welcoming Will Steffen.
Right, thanks very much, Suzanne, and thanks very much also to Vector for supporting my trip across the Tasman. It's always a pleasure to come over here and experience a bit of sanity after the politics in Australia. So tonight I want to take you on a tour of the Anthropocene, describing what it is, how we got there, and of course the question there, where on earth might we be going in the Anthropocene? So let's dig right in. I'll have to use this to move the slides. There we go. So the point I want to start with is the context, and that is that our planet is a single system, which is counterintuitive for most academics like myself, like I was raised. We talk about hydrological systems and climate systems and social systems and political systems. But in fact, all of these are intertwined, us humans included, in all of our systems into the Earth as a single system. And we've been studying this now for about the last couple of decades as a single system. And one of the things we start with is this data. This data comes from Antarctica, from the Australian Antarctic Territory in the east. It's actually an ice core drilled by the Russians called the Vostok Ice Core. And that jagged red line is actually a measure of Earth's temperature over 400,000 years. That 400 means 400,000. And you can see it's very regular. Oscillations between long, jagged cold periods and short, warm periods in between at about 100,000-year intervals. Very, very regular pattern. It's important for us because the entire history of fully modern humans is embodied in that ice core. We evolved in Africa about 200 to 250,000 years ago. We've been through 2 cycles of ice ages and warm periods. So I'm just going to now go into more detail on the last 100,000 years of that record. So in this part of the ice core, you can see that the last warm period, the one we're in now, or I should say the one we have just left, is unusually long, and it's stable compared to the Ice Age, about 12,000 years. And the geologists call it the Holocene. This is really important for humanity because until that sweet spot of 12,000 years, we were only hunter-gatherers. We had spread to many continents by 12,000 years ago, but we were only hunter-gatherers everywhere we were, whether it was the Americas, Europe, or Africa itself. So this has turned out to be exceptionally important. It's only during this period we've developed agriculture, villages, settlements, larger cities, complex civilizations, and the complex globalized world that we enjoy today. Well, a number of us were looking at what's happening in this last couple hundred years. And so what we tried to do to understand how humans ourselves have changed is to look at what we call the human enterprise. And we challenged ourselves to say, if we only had 12 indicators that represented all of humanity, who we are and what we do, what would you do? Well, you obviously have population in the upper left. You have economy. You have energy use. You have investment. You have resource use, and you have communication. Each of these graphs, it's a bit hard to say, start at the year 1750. So they start just before the beginning of the Industrial Revolution, and they go out to the year 2010. So you can see that the shape of these curves is really unusual. We thought they might be a fairly linear curve, but they're not. Not much happens until 1950. And then in 1950, there's an absolute explosion of human activity, whether it's population, economy, resource use, and so on. And some historians have called this the great acceleration of human activity. And of course, this has yielded many benefits. We're living longer. We have better medical care. We have much higher standards of living. Many millions of people have been brought out of poverty during this time. So in fact, this has benefited humanity quite a bit. But then the question as Earth system scientists we asked is, well, what does this mean for the rest of the Earth system? Can we see any evidence of any change in it that corresponds with what humans are doing? So we did the same thing for the natural Earth system. Same thing, 12 indicators, starting from 1750. The top 6 of those 12 are what we call the geosphere, the non-living physical part of the Earth system. The famous greenhouse gases on the top, and then stratospheric ozone, climate in the middle of the second row, ocean acidification. The bottom 6 are the biosphere, and this is a recognition, following on from James Lovelock's work on Gaia, that the Earth is a single intertwined system where the biosphere plays just as strong a role as the geosphere. In fact, it provides very strong stabilizing feedbacks. But look at the shape of those curves. They look reasonably similar to the first lot of human ones. So we see again from 1950 that things start to change quite dramatically in the rest of the Earth system. So we did a lot of digging in scientific papers to understand what these actually meant. And 2 things came out of thousands of papers that are on aspects of this. One is, this is not natural variability. The dominant factor driving all of those changes, whether they're in the coastal zone, the marine zone, the atmosphere, the ocean, the dominant driver are human activities. This is not natural variability. The second thing we can say for certain is that all of these are now outside of the Holocene norms, outside of that 12,000-year period of relative stability in the Earth system. So these remarkable graphs were the ones that triggered the first statement, the first proposal, that we have left the Holocene and we are in the Anthropocene. It was this gentleman who first discerned all that in the year 2000 when he saw the precursors of those diagrams. His name is Paul Crutzen. He's an atmospheric chemist originally from the Netherlands. He's also a Nobel laureate, but a Nobel laureate for a different reason. He was one of the 3 scientists who understood what was going on with the ozone hole, what was causing it, and so on. So he's now probably more famous, and if you talk to Paul, he says his legacy will be not so much the ozone hole, but his legacy will be the Anthropocene, the new geological epoch in Earth history. So that was first proposed in 2000. It took off in the Earth system science research community and has really stuck. Now it's come into pop culture, come into the humanities, and come into everyday life. But to understand what's going on in the Anthropocene, we can do the 2 things that we did in the graphs. We can look at the geosphere, the physical part of the Earth, and we can look at the biosphere, the living part of the Earth. So when you think of geosphere, the first thing that comes to mind is climate, or physical climate more appropriately. And so climate change is probably the most commonly understood manifestation of the Anthropocene, that we have now destabilized the climate at such a rate that we have left not only that 12,000-year period of stability, we've left the entire glacial, interglacial cycling of the last 1.2 million years. Here's the contemporary record. Everyone's seen this. It goes back to 1880 when we first had enough measurements globally, observations, that we can track temperature. And you see from the mid-20th century, temperature's been rising at an exceptionally rapid rate. We need to put this in a longer time frame to understand it from the perspective of the Anthropocene. So this graph here is a 2,000-year temperature record that comes from a variety of proxies, such as ice cores, tree rings, ocean sediments, and so on. So that 0 is the Roman Empire. That's AD 0. So you can see that globally, the Earth has been on a very, very slight cooling trend. That vertical axis is in tenths of a degree, not 1 degree, tenths of a degree. So the Earth is cooled by about 1/10 of a degree over 2,000 years. And that's due to changes in Earth's orbit. And you see variability within that. But you see the spike at the end. That's that post-1950 rise in temperature that broke out of the barriers of the Holocene and is rising at an increasing rate toward much higher temperatures. The rates of change here are really important. Everyone says, well, 1 degree, and we've increased global average surface temperature by 1 degree. But what about the rates? Well, they're remarkable. If you look at the rate and rise of temperature, it's now about 170 times faster than we see in the past. And if you look at CO2 rising in the atmosphere, the last time CO2 rose sharply was at the end of the last ice age, when it rose from about 180 to 280 parts per million. But it took the Earth 7,000 years to raise CO2 100 parts per million. We've now raised it well over 100 parts per million in a bit over a century. So this is remarkable, about 100 times faster than we see in the background. So these are extraordinarily fast rates, which is why this part of the Earth system, the biosphere, is having trouble coping. It's just too fast for systems to evolve, for ecosystems to move and change, and so on. But interestingly, the most dominant impact so far on the biosphere is direct human impact, mainly through agriculture and associated activities. We've now converted over half of the Earth's land cover to look like this. So there's some remarkable figures, too, on the biosphere, in addition to those on the climate. So if we look at those, this is an interesting one, done by a Canadian scientist named Vaclav Smil. And he published this, and what he asked himself was, if you look at all the terrestrial creatures on Earth that have a backbone, vertebrates. So that's everything that lives on land that has a backbone. So that's mammals like us, it's birds, it's reptiles and amphibians. And you add up the mass of all of them, all of their weight. What you find is that we humans are nearly a third. Just our body mass is nearly a third of all animals that live on land on Earth. But even more remarkably, our domesticates, our pigs, our cattle, our chooks, and so on, they're 2/3, they're 67% of all biomass of creatures on Earth. That means all wild creatures on all continents only amount to 3% now. This is the extent to which we dominate the biosphere, particularly the land biosphere. It's been completely made over by humans, and the biomass of all the creatures with backbones are virtually all us and our domesticates. A big report came out only a couple months ago by an international organization which is the equivalent of the IPCC, but for the biosphere. So it was looking more systematically about what's happening to all aspects of the Earth's biosphere over the past couple centuries. And you can see from the title that their output was pretty disturbing. So they said, in general, nature is declining, and declining at rates unprecedented in human history. Just like we see unprecedented rates in CO2 rise, we see unprecedented rates in temperature rise, we're seeing unprecedented rates of biosphere degradation. And more specifically, we're seeing that species extinctions are accelerating. They're increasing towards the Earth's 6th great extinction event. We're not quite there yet, but we're headed toward that direction. And there was more detail there, and that's around the health of ecosystems in generally. But importantly, they did at least somewhat take a human-centric view here and say, well, we depend on the natural world for a lot of so-called ecosystem services, and they are being eroded. And they're the foundations of our economies, our food security, health, and so on. In terms of how many species are endangered, they estimate around 1 million animal and plant species are now threatened with extinction, many within a few decades. And so the web of life is getting smaller, and it's getting frayed. The geologists, too, have gotten into the act, because when Paul Crutzen said, we're no longer in the Holocene, we're in the Anthropocene, he actually specifically stated this as a new geological epoch. So that immediately threw the baton over to the geological community to say, well, these guys are a bunch of Earth system scientists, they're not geologists, do they know what they're talking about? So a few years later, I think in 2008, a group called the Anthropocene Working Group was formed. So this was actually an official body formed by the International Stratigraphic Commission to explore the Crutzen hypothesis. Have we really left the Holocene? So it's chaired by Jan Zalasiewicz, who's in Leicester in the UK, and he's assembled 35 scientists, mainly stratigraphers, but because the Anthropocene is so unusual, he actually brought in social scientists, legal people, historians, a couple of Earth system scientists like myself, to inform the deliberations. So we've been going as a committee for about a decade, and we've been analyzing not only stratigraphic evidence, but all sorts of social evidence, biophysical evidence for the Anthropocene. We finally came to a binding vote only in May this year, so it's very recent. And we asked ourselves two questions. Should the Anthropocene be formalized in the geological timescale? That is, should it now officially be stuck onto the end of that long, long timescale that goes back to 4.6 billion years, that has famous things like the Pleistocene, the Miocene, the Cretaceous, all these things? Should it be on that officially? And then the second question is, should the Anthropocene base or start date be placed at the beginning of the Great Acceleration around the mid-20th century? So we had 35 members. One member didn't vote. Paul Crutzen is an honorary member. He's quite elderly now, so he didn't vote either. So we had 33 votes. We had to get a supermajority for this to move forward, the supermajority being 60%, not 50%. The result was yes, won the formal vote by 29-4. This is as close to consensus as you ever get in the scientific community. So this was an overwhelming vote saying the evidence is incredibly strong, even from conservative old geologists. Sorry if there are any geologists here. There were a lot of young geologists on this too. Geologists said, we are convinced. Even those who came into this thinking this was a bunch of rubbish coming from pop science, they became convinced, looking at the evidence, that this is really a profound shift in the history of Earth, and it indeed should be on the geological timescale. This isn't official, yet it has to be approved by 3 bodies higher up. But importantly, the chair of the next body higher up is actually on the Anthropocene Working Group, and he voted yes. So that's a good sign that this is going to move up the system. Now, geologists don't move as fast as some of the rest of us. I think for them, a few eons is pretty fast. So we won't expect this to be formalized tomorrow, but hopefully in my lifetime we may see the Anthropocene formalized. Actually, we'll need to see it, probably see it in 4 or 5 years. What's holding it up? They actually have to find the golden spike, a single core somewhere on planet Earth that is typified by this and supported by a multitude of other cores. It could be an ice core, it could be something drilled in rock, it could be something drilled in sediments, it could be a tree ring, it could be a speleothem from a cave. They're very inventive when they look at what the record of the Earth is. But I would say, hopefully, in about 5 years, you will see a formal declaration by the peak body saying the Holocene's gone, stopped. Mid-20th century, we're in the Anthropocene. Those are some of the markers. You can see them there. All the lines sweep up from 1950. Aluminium, concrete, plastics. These are all materials made by humans. So there's no doubt where it comes from, particularly plastics. And they all show exactly the same shape. So you see that the evidence for the mid-20th century is profound. It's all over the record already. Okay, we've talked about the 2 big parts of the Earth system, the climate, the geosphere, and the biosphere, the living part of the planet. What about humans and our systems? And in fact, when I draw now a diagram of the Earth system, I don't have the traditional 2 spheres that everybody uses. I have 3. I have the biosphere, I have the geosphere, and I have the anthroposphere, humans, because we are legitimately now a 3rd major component of the entire Earth system in terms of our ability to change the system. So let's look at humans. The first thing is when we published our Great Acceleration graphs, and I was the lead author on that, we got clobbered by social scientists, quite rightly. And so these are 2 Swedish political scientists from Malmö, and they said quite clearly, from Lund actually, they said quite clearly, you guys have missed the big story. It isn't humankind or mankind in general that has driven the Anthropocene. It is the small fraction of humans, the 20%, who live in the OECD countries, who are the high consumptive societies. They're driving the Anthropocene. It was a good point, and we took their criticism very seriously. So we actually went back and redid those graphs. And they look like this. A bit hard to see here. But what we did in those human graphs, and we could do that, we had data for 10 of the 12, is we split humans. We split them into the OECD countries. That's US, Canada, it's Europe, it's Australia, New Zealand, and it's Japan. And then the middle, those are the dark brown. And then the middle color are the rapidly emerging economies, China, India, Brazil, South Africa, so-called BRICS countries. And the light is all the rest. It's all the poor people around the planet. All you have to do is look at the top left ones. In terms of population, since 1950, since the Great Acceleration, very little population growth in the wealthy world. A little bit. Almost all of it's been in the BRICS and the poor countries. But look at the GDP. That equates to consumption. Absolutely dominated by the 20% of us who live in OECD countries. So our critics were right. They were absolutely right, and the data supports it, that inequalities within the human system are really an important part of the whole story of the Anthropocene. And so then people said, well, it shouldn't be called the Anthropocene. It should be called the Capitalocene or something like this. So we have all sorts of things that are out there now. Unfortunately, Anthropocene is stuck, so it will be around. But this is an important part of the narrative. So if we look at inequalities more generally, there's an interesting story here. And this is going back now to about 1913. And we look at the English-speaking countries. And, of course, Australia and New Zealand are part of that, although New Zealand doesn't appear there. Australia does. And we look at the European countries and Japan. And what we see are very high inequalities. So that number, 12%, 14%, that's the amount of GDP that the top 1% of the population commandeers. So the higher that number, the higher the curve, the more inequality in the society, the more it's dominated by the wealthy. So what you see is very large inequality around the First World War. That got split up by a World War and a Depression and a Second World War. Things became much more equal after the Second World War. So you see, mid-20th century, inequality went way down in both Europe and the English-speaking world. But look what's happened since then. Two different shapes of the curve. Europe, mainly the social democracies, think of the Nordic countries and so on, have managed to maintain a higher level of equality, income equality in their countries. The English-speaking world has gone off in a different direction, particularly in the USA, where there's very, very strong growth in the last couple of decades in inequality. So you might say, well, what does that matter? The English-speaking countries in general have such high incomes. Does it matter that there are a few that are commandeering these enormous amounts of wealth? Well, the answer is yes, it probably does. And this is really interesting. This is some work by British epidemiologist Kate Pickett and Richard Wilkinson. And what they do here is in this graph, the vertical axis are problems, social problems. You can read what they are. They're problems that actually affect wealthy countries. They are not problems that are caused by dire poverty. The horizontal axis is income inequality. So it's low on the left, it's high on the right. What shocked them was how tight this correlation is. It cuts across cultures. It cuts across Scandinavian, continental European, Japanese, English-speaking world. And it's very tight. So the more inequality you have, the higher the social problems. The US is so bad it's actually off the graph, the only one that's off the graph. And they hypothesize, and it needs to be tested, that this is an innate genetic quality of humans. We have evolved to be highly social creatures, and that we thrive in societies that have good social systems with some inequality but capped at a certain level. Now, this is a hypothesis. It's generated a lot of debate. People argue with this. But that correlation, to me, is so strong that there must be some reason for it because it cuts across cultures. So this is part of the Anthropocene story, too, not just what's happening to the other two spheres, but what's happening within the human sphere, the growing inequalities. Others, like Ida Kubeski and Bob Costanza, who are ecological economists, have developed what they call the genuine progress indicator as a different way of judging progress rather than GDP. So the green line is the traditional GDP per capita. This is looking at, again, at the OECD countries. The purple line is a genuine progress indicator. Well, what did they do? Actually, this is quantitative. They took GDP and they subtracted off everything that actually adds to GDP but doesn't add to well-being. Think of making more prisons because your crime rate goes up. That adds to GDP. thinking of a massive flooding of New Orleans and rebuilding. That adds to GDP, but it doesn't help anybody. So when they do that, they come up with an interesting conclusion. Somewhere around 1970, we capped our well-being. And we're becoming wealthier and wealthier. And if anything, we're actually less well off in terms of our well-being. So again, there's some solid work here that's actually challenging the dominant view of ever-increasing economic growth. So this leads us now, as Earth system scientists, to look at what are the incompatibilities, because the Earth is changing so fast in all these different spheres. And we can certainly see it in the social sphere today. But certainly we see it in the geosphere. We see these beautiful circulation patterns in the ocean and the atmosphere. And stamped over that, we see circulation patterns which require enormous amounts of energy. This is shipping and air travel around the world that's superimposed on night lights. Enormous amounts of energy being expended for this circulation pattern of Homo sapiens. The land surface, the terrestrial biosphere. A lot of people still think there's a lot of Earth that looks like this, like the savannas of Africa. In fact, there's very, very little of this left. Increasingly, the Earth looks like this. It's dominated by humans. Still has an ecosystem, but it's a highly managed ecosystem with little pockets of natural ecosystem. And, of course, we have social issues. We still have somewhere around 800 million people who are in abject poverty and need to come out of poverty at the same time that inequalities are growing and urbanization is growing at an enormous rate. So, again, we have system incompatibilities developing all throughout the Earth system. And this is why we see so much instability. We see instability in the climate. We see extreme weather events that are happening around the world. We're seeing a lot of disruption of the biosphere. Extinction rates are going up. And we're certainly now seeing a lot of instabilities in human systems. We're seeing a lot of variability. Think of the United States. In one election, it went from Barack Obama to Donald Trump. In one election. That's showing huge variance in a political system. We're seeing the hollowing out of the middle in Europe. The last European parliamentary elections, the Greens and the left went up in vote, and the far right went up in vote, and the center hollowed out. These are symptoms, from a complex system point of view, of a complex system where the variance is increasing, and it may be close to a tipping point. So it asks us the question, then, where is the Earth system going? Because these three parts now, the geosphere, the biosphere, and the anthroposphere are now tightly intertwined, and we have to understand how all three of them interact to understand where the system is going. So let's take now a longer-term Earth system perspective on the climate, on the temperature rise. Many of you may have seen this. These are the IPCC climate model projections out to 2100. So you see the time scale there is from 1900 to 2100, 2 centuries. And you see the divergence, and that depends on how much more we emit. So there's low emission lines, which are the blue, high emission lines, which are the red, couple in between. But the dominant underlying assumption that everyone just takes for granted is the dominant factor up to 2100 at least in driving climate will be human emissions. But that's a simple cause-effect logic. It's not a complex system view. So some of us are now challenging this. And we do this because we look at what this actually means. There's our 2,000-year temperature record from the Roman Empire. You see the spike emerging at the end, the human emissions. Now notice that 1900 is way off to the right, 2000. 2100 isn't very far to the right. So let's map those IPCC projections on, and it looks like this. So when you map them here, you see this is an enormous spike. By the way, see 4 degrees up there? That's the difference between an ice age and a warm period. Ice ages are, on general, 4 degrees colder than a warm period in global average temperature. So we're talking about a potential rise as big as an ice age, but in the opposite direction. Ice ages take 7,000 to 8,000 years to transition to a warm period. This is a century or two. So these are enormous shocks to the Earth system. Last time we saw shocks like this was about 56 million years ago, with an enormous outgassing of methane from ocean sediments. So we're committed to about 1.5 or 2, the Paris targets. That's the best we can hope for. And we have a challenge to meet those. And we actually have to meet those, in my view. But if we go up to 4 degrees, which is the high emission scenario, that's actually a completely different Earth. And we'll get there very, very fast, faster than the natural world can adapt. And a lot of people argue faster than humans can adapt, even with our powerful civilizations. But I think there's a joker in the pack that even most scientists are ignoring, and that's this region between 2 to 4 degrees Celsius. And that region is it accessible? Some of us are saying, no, it isn't accessible. Why? Because there are intrinsic feedbacks and tipping points in the Earth system that once you hit 2, may take you to 4, even if emissions go to 0. What do these look like? Well, we've now been able to map them on the Earth system. There you see them color-coded. There are 3 different types. The bluey ones are ice. That's melting ice up at the poles. The red ones are circulation changes. For here in New Zealand, the ENSO, El Niño Southern Oscillation, is really important. And the green ones are changes in the biomes, like the Amazon basin and so on. Now, this figure was drawn, as indicates, in 2011. It was hypothetical. Since then, we have evidence that, in fact, some of these things are already changing. So we've seen 2 big droughts and fires in the Amazon. And by 2012, we were able to publish the fact that we've lost 10 years of carbon storage due to that combination of deforestation and climate change. The permafrost up in Siberia contains an enormous amount of carbon. We could lose up to 50 to 250 billion tons by 2100. Again, that adds CO2 and methane to the atmosphere. We're starting to see bubbling up now as that warms at about twice the global rate. Arctic sea ice, that's the floating ice on the ocean over the North Pole. We think that's already crossed a tipping point. That's being lost during summertime at an increasing rate. Coral reefs, we may have crossed a tipping point there. Certainly at 2 degrees, everyone says they're finished, they're extinct. 1.5, maybe some remnant reefs left. So even under the Paris climate targets, we may have crossed the coral reef tipping point. Greenland, that's the rate of ice loss from the Greenland ice sheet increasing. Same with West Antarctica. So these aren't fanciful things drawn by scientists in their rooms. The things that are actually happening in the real world. The most recent research says that these may be connected, like a row of dominoes, where you start tipping the first ones at 1 to 3 degrees. They increase the temperature. You tip more at 3 to 5, which increase the temperature. So it's actually the linkage of these tipping elements that may lead to that 2 degree, 4 degree transition without humans. So this is the latest science, but it's actually completely consistent with the way a complex system should behave. We drew a little cartoon in the paper on this to help people understand the complex dynamics. This is an oversimplification, really, of a complex system diagram, but nevertheless, it gives you the idea. So think of this as a landscape out there in the world. So when you see valleys, that's a stable place. When you're up on a ridge, you're unstable. You could roll over one side or the other. And so time comes from the back of that down toward the present. So on the left, you see the ice ages. You see those deep valleys that the Earth sits in for 70 or 80,000 years. And that little notch where it sits up there at the top, that's those little warm periods that are fairly short. So that's what that valley and little upper valley are representing, that oscillation between the ice ages and the warm periods. And that's what we've been doing for 1.2 million years. But the next Earth that's out here in this sort of very undulating landscape, not very well defined, that's what we are today. We're out of the glacial interglacial cycling. We are not going into a new ice age no matter what. That's already gone. And we're not going to go back to the Holocene. That's gone too. So we're out in no man's land. That's where we are with rapid biodiversity loss, 1 degree warming, and so on. So we can depict that in our little diagram with this graph of where we are now with that temperature spike in the upper right. So now our real challenge is all is not lost, but we actually have to realize that we're in control of where this Earth is going. We're the dominant driver of change. And I think we're soon coming to a bifurcation point where we can have a choice of going on Earth system stewardship, that's getting our act together, meeting the Paris targets, becoming regenerative in terms of the biosphere, dealing with equity issues, and so on. All those tools are there. So that is still available to us. We call it stabilized Earth, because it's actually not a natural valley in their system landscape, one that has to be created by us. But we actually do have the wherewithal to do this, to steer the Earth over to a stabilized Earth. If we don't, somewhere in the future, and we don't know where, somewhere in the next few decades, we may cross a tipping point that starts us rolling down a valley. And that valley takes us toward this tipping cascade that I just talked about, drawn here as a planetary threshold or a cliff. And you roll down and you fall in. And hothouse Earth, that we nicknamed it, is actually extremely stable. We know the Earth, millions of years ago, has been in a 4-degree warmer world, and it sits in there for a few million years. Very stable, but not very good for us or other large mammals. So the point is, we haven't reached that bifurcation point yet, but I think we have enough science to know that it lies out there somewhere. And our challenge, of course, is to grab the changes that are occurring rapidly already in terms of technologies, in terms of social systems, and say our challenge now is not to become ever wealthier. Our challenge is to steer our planet into a safe landing, which is what stabilized Earth represents. So just to convince you, you don't want to muck around with this, we've done some estimates of what hothouse Earth looks like. For you in New Zealand, think of sea level of 20 to 40 meters higher. It's not going to happen overnight. It may happen at a rate, though, as much as 2 meters a century, which is pretty fast. Carrying capacity, maybe 1 billion humans. So people say, oh, well, humans will go extinct. Probably not, but it'll be a pretty rough ride from 7.5 billion down to 1 billion, and so on. So it's not a good world. I've actually started to see people simulate with models what Earth would look like with huge zones of inhabitability at 4-degree world. So I don't want to dwell on that because it's not a good future, but just to say you do not want to go to hothouse Earth. How plausible is this? Do we have to take this seriously? Yes, we do. Complex system behavior, we know the Earth behaves this way. Hothouse Earth conditions are accessible with the CO2 in the IPCC reports. So if you go to the RCP 8.5, which is the high emission scenario, you get to hothouse Earth. The only difference we're saying is you may not need to do all those emissions by humans. Many of them may be internal to the Earth system. And indeed, some of the feedback processes already operate in glacial, interglacial cycling. Where does this lie? If people ask me, I would say we're safe below 1.5. I don't think we're going to start this cascade at the lower Paris target. I think at 3 degrees, we're almost certain to. And that's 3/4 of the way to hothouse Earth anyway. And we don't know where in between. So it's a matter of risk goes up when you go from 1.5 to 2. So this adds another, I think, element of sensibility to the Paris climate target. So when countries in 2015 actually said, and interestingly, you remember what the trigger was for that was? The trigger were the small island states who jacked up at what was going on and said, hey, listen, if you guys are talking about 2 to 3 and you may muddle through, we won't. We'll be gone. And so they pushed and pushed and pushed. And they finally got agreement of 1.5 to 2. That was before a lot of this science on hothouse Earth was done. So it looks like they had it dead right, that that's exactly what we need to aim for. Aim for 1.5, get as close as you can to that. So it's a very important development. What are the signs of hope? There are actually a lot of signs of hope. I could spend another hour and a half about exciting technologies which are coming on board. But we need the right social changes to embrace the technologies and the social changes that are needed. Interestingly, the students are taking the lead. This is Greta Thunberg from Stockholm, who even just less than a year ago sat down outside the Swedish Parliament in October, only herself, every Friday, wrapped herself up to get through the Swedish winter, on strike. Less than a year later, 15th of March, which of course is not a good day here in New Zealand, but 15th of March was the massive school strike. We estimate between 1.5 and 2 million school students around the planet struck for climate change. It ranks in the top 10 of global civil action ever, as far as we can say. Less than 1 year, one person started it. It gives you hope that we can trigger social change fast. Greta doesn't mix her words. And she says quite clearly, we're sacrificing our civilization so a few people can get even wealthier. So she's attacking our socioeconomic political system at the core and saying that really is what the ultimate problem is. And she says it very profoundly, you are stealing children's futures in front of their very eyes. As I said, this is spreading around the world. I happened to be in Stockholm on the 15th of March, doing some work with my colleagues at the Stockholm Resilience Center. So I went down to the student rally. This is taken from what now may be a sacred site in Stockholm. This is the site where Greta first sat down. The building in the background is the Swedish Parliament House. So instead of a single 15-year-old girl on the 15th of March, there were about 20,000 Stockholm residents. And I would say, I was there, about 75 to 80% of them were girls, young women, mothers, and grandmothers. They dominated, and they had some profound messages to say to all of us. And some of the students were saying, look, when you adults start behaving like children, we have no choice. We have to behave like adults. Well, that's pretty profound, isn't it? And this last one, you're running out of excuses, and we're running out of time. This we're running out of time is now a common message that's coming across. It's coming across from Sir David Attenborough. It's coming across from the growing number of jurisdictions that are declaring climate emergencies. And they're doing it not because everything's going to fall over tomorrow, but we're running out of time to make the changes to deliver the outcome in time. Okay, I think really the fundamental issue we're facing now is in the Anthroposphere. And it's an issue of really who we are, how we really operate as a species and as a society, and what are our values, and what do we need to change to drive the new technologies. I should say to embrace the new technologies. A lot of the tools to actually get to stabilized Earth are there. That's really positive. But a lot of people are arguing we need fundamental change. Highly recommend this book, The Systems View of Life. This goes from the first single-cell organism that arose on planet Earth. A beautiful, beautiful, consistent story of the biosphere and its development. But then they talk about humans and say we're dominated now by a global economic system that's actually what they call predatory capitalism. We're the only species that actually destroys its own habitat to make some people wealthy, of course. So this is a profound statement about where we are really going. There are good solutions, though. Kate Raworth, who's a colleague of mine from University of Oxford, has done some fantastic work on how do you redesign an economic system to actually deliver well-being for humans and to become good stewards of planet Earth. She calls it a donut. So if you look at the inside ring of the donut, that's what we need as humans. We actually need to have jobs. We need to have education. We need to have income. We need to have all this stuff. Importantly, we need more gender and social equity in our systems, which she puts in there explicitly. So that's what economy is supposed to deliver, and a social system is supposed to deliver. And that's what we strive for, imperfectly, of course. What we've forgotten, and that's because until recently, we didn't need to worry. The Earth was so big that we didn't need to worry about it. So we are no longer a small world on a big planet. We're a big world on a small planet. So that means we need that outside ring. And those are the 9 planetary boundaries that give you guideposts for how much you should or shouldn't change the Earth system and keep it in a stabilized Earth state. So now we have the donut. We need to have the floor of social well-being, but we need to have the ceiling of environmental integrity around the planet. And she has a lot of good ideas in her book. She has 7 major principles to deliver a donut economic system. I only put 3 here, but it's really important. One is systems thinking. Present-day economies are not systems thinking. They grab resources, metabolize them, we consume them, and out goes the waste. That's a linear chain. There's a lot of discussion now about circular economies. That's systems thinking. So we need to go to systems thinking right throughout our economy completely. And she calls it dynamic complexity. We need to generate equity, and it needs to be by design, she argues. That is, right now, how do we get equity? Well, we have growing inequality, and then governments are called upon to redistribute wealth to the poor people. And that's contentious politically and so on. Government shouldn't have to do that. The system should deliver equity by the way it's designed. And same thing about the biosphere. I'd like to ban the word resources, actually, because that's most of the resources we're talking about are ripping stuff off the geosphere or the biosphere. We need to become regenerative by design, so our economies actually build well-being for humans at the same time they regenerate the planet. And she has some good ideas about that. Value systems, philosophers get into the act. Humanities have a lot to say about how we navigate the Anthropocene. This is one from University of Chicago, originally from India. And he says, look, our problem is, particularly post-industrial revolution, we have developed a human-centric way of viewing our societies, our economic systems, and the planet as a whole. But really, the Anthropocene demands that we become life-centric. It's not all about us. It's about the biosphere and the fact that we have a living planet. So we need to change the way we fundamentally think. I'll give the final word to Indigenous Australians who have the longest continuously living culture that we know of on planet Earth. It goes back at least 65,000 years. And they really have, I think, a good guidance system for how you live, even on a tough continent like Australia. And you can see what they say. They have a systems view of themselves and of their role in the planet. Our job is to look after country, is what they say. We're a tool in the cycle of things. We go out into the world and keep the balance of nature. It's a big cycle, going out into the world, going back to it. I want to conclude now, though, with a positive note of how do you actually deal with all this complexity, all these huge questions? Well, you deal with it by looking at your patch of the Earth. And one of the big pleasures I've had over the past decade is being involved with the Canberra ACT government when in 2011 they decided, by the way, pushed by students, well before Greta. We had a group of Canberra students who injected themselves in the 2011 election and said, we want Canberra to reduce emissions by 40% by 2020. Well, the government that said, well, yeah, we'll do that, got elected, and they delivered. So Canberra is now 100% renewable, 2011 to 2019. Our emissions have dropped 40%. It was controversial. The Treasury of the government fought it tooth and nail, saying it's going to kill our economy. Canberra's economy has benefited. Wind companies have moved their headquarters in. We have some of the lowest electricity prices in Australia. Now, we've gone to the government just this year, earlier this year, and they've legislated with approval of Treasury to be net carbon zero by 2045 out of the total economy, and they've legislated 5-year targets. Transport, built infrastructure, waste, everything. And I've done the calculation with a carbon budget. That brings Canberra in. If everyone did what Canberra did, we'd be at 1.8 or 1.9 within the Paris region. So the news is, all this is what I'm telling you is we don't have a choice, I don't think. We actually have to make the changes. The good news is the tools are increasingly there to do it. And the models are increasingly there that we can do it. So our job is we have a couple of years left, really, to decide that we're going to do this. And then after that, we have 2 or 3 decades to deliver. So as Sir David Attenborough says, time is running out. We actually have to deal with this. So let's get on with it. We can do it, but we can't wait any longer. Okay, thanks very much for your attention. Hopefully we'll have time to do this.